JS, we're going to start the last day of the conference with Denis BERNARD from ENS Paris with a talk about microscopic fluctuation theory. Can it be quantized?
Merci, Ina. Okay, so it's a pleasure to be here, back in Saclay for Hubert Fest. So I am going to talk about macroscopic fluctuation theory and something we did with, I did with over the last few years with a number of collaborators. Fabien is here, Michel is time to time in here, and you can read the other collaborators. But before, I want to say a few words about Hubert. So we met long ago when we were in École Normale. Not at this time it was in Saint-Cloud, and then this École Normale moved to Lyon. And in particular, during 1 year, we were preparing some exotic exam to become a teacher, high school teacher, which is called agrégation. And we had to prepare, how you say, experimental practical work in order to present them. That was part of the examination, and we were working in pairs, so I was with Hubert. So I don't know which picture is a more faithful representation of what we are doing, but we developed very useful skill, which I hope maybe one day we will be able to use in a future collaboration, because up to now we didn't write any paper together, so maybe one day, I hope. Okay, so it was long ago. So now I will try to talk a bit about science. So the question we ask is, can we formulate a quantum analog of the macroscopic fluctuation theory? Which means that we would like to see if there is some universality in the fluctuation in a diffusive quantum many-body system. And the universality we look at in the fluctuation is for quantities which are typically quantum, like entanglement or coherences, not only for transport, which is more related to classical theory. So that's the question we ask. So there has been many progresses in the last few years about transport and even coherent effect in quantum many-body system out of equilibrium. But most of these progresses are related to systems which are mainly ballistic, because they come from studying integrable systems, which was leading transport behavior is dominated by ballistic phenomena. So if we look at diffusive system, it means that we have to, and we want to study coherent effect in diffusive system, it means that we have to look at systems where there is coherent processes in order to talk about quantum mechanical system, diffusive, so it means that they have to interact with some other degrees of freedom. So say differently, we have to study the system at a mesoscopic scale, I mean at a scale which is bigger than the mean free path, but smaller than the coherence length, which is the scale above which you lose all coherent effect. And we have to study such a noisy processes in such a system in order to study the fluctuation. And what I will discuss is a very simple model which deal with this phenomena, and as you will see, there is a nice and rich structure in this model. So maybe I will remind you what macroscopic fluctuation theory is. So it's a classical theory which is adapted to describe fluctuation in locally diffusive classical system out of equilibrium. So it means that it's since it deals with transport, it's described by a local conserved quantity, which is with the local conservation law. So here I define the quantity as a density. So there is not a pointer. So the system is described locally by a density, which I denote n, and there is a local current, which are linked by a conservation law, and that's the transport. This is the transport of this density that you look at. And since the system is diffusive, this means that the current, forget about this term, the current satisfies the Fourier fixed law, depending on which country you are. So here it's called the Fourier law, and which just says that the current is proportional to the density. The way the macroscopic fluctuation theory is to say that you deform this Fourier law by adding noise, and then the noise is very simple. It's proportional to the white noise in space and time. And from the statistic of the noise, this induces a statistic on the density, on the current, and this is this density that you want to study. This is the fluctuation, the distribution of this fluctuating quantity that you want to study. But the distribution of this quantity is completely induced by that of the noise. So from this formulation, you can extract transport property, mean transport property, but also the deviation from this mean transport property, which are fluctuating. Now, the way it's formulated, usually it's via large deviation function. So since you are in a macroscopic system, the fluctuations are tiny when the system is big enough. And this is reflected that the noise is small because it's proportional to the square root of the inverse of the length of the system in 1D. So as a consequence, the probability of fluctuation away from the typical mean behavior is exponentially small. So what this large deviation function describes is a rare event, which are subleading the system size away from the mean behavior. So that's the kind of formulation we would like to make in quantum system, where we would like to describe rare fluctuation of typically quantum quantities away from the main typical characteristic of the system. And in the macroscopic theory was defined 10 years ago by a group in Rome, and it emerged from different studies, but in particular from study of simple microscopic model, and the most well-known is a SEP, which is a model of a particle moving on a line, moving either to the right or to the left, or defined on a graph, and with the only property, so it's a stochastic move, with the only constraint that there should be no particle, at every time there is never two particles on the side. There is either 1 or 0 particles. So when you ask a question of what will be the quantum analog of the macroscopic fluctuation theory, then the first attempt could be just to quantize the theory. So you have a classical theory, and then you promote all quantities as operators in quantum theory. So the first one is easy to imagine. So you have a local operator, which is the density, a local current, and satisfy the conservation law. But then the second one is, if you forget about the noise, is a Fourier law. And this is a constraint, which in a quantum theory will become a relation between operators. So it's a bit difficult to see how you can implement it. And another, then the second question will arise is what will be the nature of the noise in the quantum theory. It's not really clear. And even if you answer these two questions, you are never sure that when you will quantize the classical formulation, this will describe the quantum property of a quantum many-body system, locally diffusive. So we took another route. Actually, we started to this route initially, but didn't go anywhere. So and so we look for a simple model where many-body system which interact with extra degree of freedom in order to induce diffusion, and keeping track of all the the coherent processes. So this forces us to look at, again, as I said, diffusive system for many-body system, but coupled to coherent, noisy, stochastic processes in order to be able to study the fluctuation. And what we want to do is to describe this system a bit away from the standard hydrodynamic description, because when you do hydrodynamic, you always assume that at some hydrodynamic scale, so if you look at the system on a small microscope, in between macroscopic and mesoscopic scale, the reduced density matrix of the system is thermalized. So it's diagonal in some bases related to the local quantity for which you may look at the transport. So if we want to look at coherent processes in many-body system, we have to keep track of the off-diagonal element of the density, reduced density matrix. So we have to go a bit beyond hydrodynamics. So there is not yet such a description. So as I said, we look at very simple model, and we hope that the model we look at are generic enough or universal enough so that we will learn something on what could be the possible formulation of the quantum analog of the macroscopic fluctuation theory. A bit as it was done in classical theory, where people look at SEP or other exclusion processes, and from that learn what will be the possible structure for the macroscopic theory. So now I will discuss about quantum analog of simple exclusion processes, which we call quantum SEP if it's symmetric, quantum ASEP if it's asymmetric, but I will only discuss the symmetric one. So now I will not tell you what is the macroscopic quantum analog of the macroscopic fluctuation theory, because I don't know yet, and I will just discuss this simple quantum SEP model, which is just a simple model of free fermion, if you want, on a line. It can be on a graph, but the hopping amplitude is random, stochastic. It's noisy. So it means that the amplitude, which is denoted here, so this is Hamiltonian increment to when you want to evolve the system from time t to t plus dt. So it codes for hopping of fermions from the left or to the right, with an amplitude which is given by a Brownian increment between time t and t plus dt. So if you want, it's a Gaussian variable. So there is two complex numbers which are distributed according to the Gaussian distribution. And they are independent from time step to time step. So it's really a stochastic process. And so that's plus. So there is two possible ways to formulate the system in 1D. Either it's a closed system, so you define it on a loop, or it's an open system, and you have a way to inject or extract particle fermions on the two boundary of the interval. And these are described by some processes that I will maybe discuss a little bit later. So this is one of the simple models, because if you look at the equation of motion of, let's say, the local density operators, the number of fermions at a given site, so it satisfies an equation which is like the Fourier law. So it's a diffusive equation. The current is proportional to the gradient of the density, plus some noise term, which take value in the algebra of operators. So it's some kind of quantum noise, if you want. So it's really one of the simplest models of quantum fluctuation diffusion in many body system. So it's not, diffusion is not only at the level of the correction function, but also at the level of the operators. And why we study it? Because it's a very simple model. It means it's a Gaussian model for each realization. If you start to look at the mean behavior of the fluctuation, it's not a free model, because you have to average over the different noisy realization of the noise. But at least it's free for each realization, which means that you can discuss all properties in terms of the two-point function, so reduce the number of variables from an exponential number of parameters to a polynomial number of parameter polynomial as a function of the size of the system. And as I said, I will discuss two formulations, one which is closed, in which case the system converges to equilibrium plus fluctuation, and one where the system is open, in which case the system is out of equilibrium, there is a current plus fluctuation. So why it's called SEP is that, as Fabien said yesterday or the day before, if you look at the mean behavior of the density matrix, so the density matrix evolves according to the Schrödinger equation, but with an Hamiltonian which is time dependent, noisy and time dependent. Since the Hamiltonian is random the density matrix become random after a one-time step or any time t bigger than the initial time. And so you can look at the mean density matrix. And what you can prove is that if initially your system is diagonal, the density matrix is diagonal in the basis of fixed occupation number, it will remain so in the evolution, in mean. And the evolution equation, which is of Lindblad type, is exactly of the SEP. So this means that in mean, if you start with a diagonal density matrix, you are just describing SEP. So this Lindblad equation is the same thing as the Markov equation, evolution of probability in SEP. So in mean, you have just a SEP, so it's why we call it quantum SEP, and we call it quantum because there is a bit more, it's a quantum effect. So you, for example, you can have superposition, you can consider states which are superposition of classical configuration. And there is interferences effect between these classical configuration. And the way to test these coherences or interferences is to look at the higher moment of the density matrix. So the density matrix is a random variable. You can look at the cumulants, higher moments of the fluctuation. For example, if you want to look at only at the quadratic fluctuation, you will look at the expectation value of the product of two matrix elements of the density matrix. And all these cumulants satisfy also an evolution equation, which is the analog of Fokker-Planck equation, which is of the Lindblad type. So, and this Lindblad type can be described by a spin chain, which is not trivial. So even though the model is free, in mean, for a higher moment, it's a non-trivial spin chain. And so to learn property of fluctuation of the higher moments, you have to study this higher speed, this collection of hierarchy of spin chain. Okay, I forget when I started. Huh? So now I will just describe what are the main property, some property of the model in the closed and open case. So in the closed case, so your model is defined just by opening term, so on a loop, on a circle. So there is no injection or extraction processes. And as I said, you can code for the property of the system just by looking at the two-point function, which is, again, a random variable, the two-point function. It's a matrix, which is random. And the first thing we can look at is at the steady properties, meaning that the property that you will reach at very, very long time. Okay. So what you can expect, or even prove, that at very, very long time, the distribution of this matrix becomes stationary, and you can compute the stationary measure, or at least the first few cumulants. So if you look at the one-point function, so there's the mean of this two-point function, which is linear in the density matrix. So this is described by the mean density matrix, which I say is like SEP. What you can prove is that the diagonal component of this density matrix, which is C dag at one side, so it's just a mean of the quantum expectation value of the number of operators. So this is non-zero, and it's uniform. It's just given by the number of particles divided by the number of sites. So it means that in mean, you reach a uniform state, equilibrium state, as you expect, because it's closed. And then the off-diagonal in the steady measure at long time is 0. And this just reflects coherences. You don't have off-diagonal elements in the density matrix. So in mean, whatever density matrix you start with, you will converge to the diagonal one, which is, and this is a fully mixed density matrix fixed in the sectors of a given number of particles. Then you can look at the two-point functions. It means that look at the expectation value or the covariance of the J, so the product of 2J. So this is bilinear in the density matrix. It's not anymore described by SEP, by the classical SEP, because it's quadratic in the density matrix. So again, you can prove, can compute what it is just by looking at stochastic equations that J satisfy. And in particular, you find that in mean, the off-diagonal matrix element, Jij, so here I is different from J. So in mean, this is 0. But if you look at the the variance. This is non-zero, and the variance scale like 1 over L. So it means that fluctuations are effectively subleading in the size of the system. And the prefactor is the initial homogeneities in the density. So it means that if you have initially a non-uniform density profile, then you generate coherencies which survive a very long time. So they are subleading in the system size, but they survive. So if you have a uniform one, of course, because you are at equilibrium, you will remain at equilibrium and you will not see the coherency. But if you have a little bit of inhomogeneity, that's enough to generate coherencies during the dynamical processes, random one, and they survive. They don't die off. In infinite systems, they are zero, but in finite systems, they are non-zero. So this is a bit analog to the classical macroscopic fluctuation, where the fluctuations were subleading in the system size. They are rare, so they vanish for infinite system size. Here, these fluctuations, these coherencies are non-zero. They scale like 1 over square root of L, and they have rare. The fact that they scale like 1 over L means that for large systems, they have rare fluctuation away from zero. And so it means that what you can prove is that at very large time, with a huge probability, converging to 1 when the system size goes to infinity, you converge to the equilibrium density matrix, which is just the Gibbs measure with the only quantity which is conserved for each realization, which is the number of particles, up to fluctuations, which are very rare, and for which you can describe the large deviation function. So we know the large deviation function of this fluctuation, because actually we can map this invariant measure to random matrix theory. Then, so that's an overview of
what kind of random
the unitary one, standard one. So what I will maybe that if you look at the generating function, that's the random variable, so you can define the generating function for it. And the generating function is equal to the Hutchinson-Zuber integral. So if you want at this invariant measure, if you fix the number of particles, and you start with a pure state, since the dynamic is unitary, it will remain a pure state, and a pure state with a fixed number of particles, and you can describe the measure by saying what is the distribution of these states in the sector of fixed particles in the invariant measure at right term. And this is just the R measure, the one induced by the R measure. The unitary group acts on the sectors of, it acts flexfully on the sector of fixed number of particles. And from an R measure on the unitary group, you induce a measure on the representation. So in the open case, the way the model is defined is that you have still the noisy processes in the bulk, and you inject particles and extract particles on the two sides. And as for SEP, we inject with some rate. So there is a rate for injecting the particle on the left and one on the right, and there is a rate of extracting a particle on the left or on the right. And in quantum mechanically, these processes, they have to be dissipative because you inject particles and they mimic the contact with reservoir, so they are described by a Lindblad equation. So it means that for each realization of the process, of the evolution now, the dynamics is not only unitary, it's unitary in the bulk, but there's still the dissipative processes on the two sides. And you can ask the same question. I will talk a bit about the dynamics for the closed case later, but you can ask for the same things. What is the distribution of the quantum observable at very, very late time in this model? So it means that study the invariant measure of the model. And first, you can look at the mean. So again, the model is completely described by the two-point function because it preserves Gaussianity of the states, the dynamics, even the dissipative processes. So you describe everything by the matrix of two-point function. You can look at the mean of these matrices, which is correspond to look at the mean density matrix, which also again will be described by SEP. And you have the same output as in the closed case, in the sense that the off-diagonal matrix element of J in mean vanish, which is still decoherence. And as for the classical SEP, the mean density matrix is described by classical SEP. So the expectation value of the quantum expectation value of the density operators is non-zero and vary linearly between two densities that we have imposed by the injection rate. So it means that you have a non-linear profile. It's not at equilibrium. Since the current is proportional to the gradient of the density, you have a non-trivial current. So you are effectively describing the system out of equilibrium. And then you can look at the fluctuation. You can look at the first as a variance, the product of two. So this is linked to the property of the two copies of the system, tensor product of two copies of the density matrix. And once again, you can show that the off diagonal matrix elements are non-zero. If you look at the variance, they scale like 1 over L times something which is proportional to the imbalance of the densities that you have imposed, plus something which reflects long-range correlation along the shell. And the fact that it scales like 1 over L calls for the same thing. You have rare fluctuation away from the mean typical states, which calls for the current. And then we can try to construct the invariant measure, which will amount to have an information on the any product of copy of J. So here I take n product of J. And what you can prove is that the leading contribution to this cumulant scale like 1 over L to the power n minus 1, if n is the number of insertion of J, which ensures that there is a large deviation function, this scaling. So there is a large deviation function as it's a classical SEP, which codes for the fluctuation. And this correction function now depends on the point. So in the closed case, it was purely topological. The steady measure was independent of the point, except from the topological information whether the point coincides or not. Here, there is long-range correlation, so there is a non-trivial dependence on the point, and we know we have some information on them that I will maybe discuss. So it means that we have some n on the steady measure. So now where we are in this study, so as I said, in the closed case, we have a control of the steady measure because we map it to random matrix theory. In the open case, the steady measure, we have information on the function which I call G, which codes for the correlation. We have some combinatorial information, but probably not yet enough, and I will say a word. Then we look at a typical property which is related to, which is typically quantum mechanical. So we look in particular at entanglement entropy. So in the closed case, we know a large deviation function for the distribution of the entanglement entropy of a subsystem. We know that in the closed case by using random matrix theory. We did that with Lorenzo Piroli, who is not here. In the quantum case, we don't know yet. And then more recently, we did, I think, a step toward defining a macroscopic fluctuation, analog of the macroscopic fluctuation theory, which I call quantum mesoscopic fluctuation theory, which is that we look at the dynamic of the fluctuation. So we look at the fluctuation evolve with time and reach a steady behavior that we know. And we have shown with Fabien that there is a regime where those fluctuations, a regime of time on scale, where those fluctuations are described by a scaling theory. So you can take the continuum limit. And the evolution equation for this in this scaling theory is mainly diffusive, so the density diffuse. But if you look at the evolution of the coherences, it's diffusion plus relevant correction from that. And we are working on the open case. So I think this is the first step to defining the mesoscopic fluctuation theory as in the continuum. So instead of describing the technique to how we prove these kind of things, I would like just, since it's a conference on mathematical physics, I would like to mention a bizarre connection that we don't understand much. That's surprising, so there is nothing. When I sent the file, there was something. Il y a une erreur, on avait deviné. Ouais. Bon, c'est moi. So I will do it in Blackboard. Yeah, may I do in Blackboard? Maybe I need my iPhone. So if you take at, so if we look at the system, if we look at all the correlation function, I was telling you that the leading behavior is 1 over L squared times a function which is finite in the scaling limit. Okay. Now this. So you can take the point, no, they are supposed to be distinct. So you take this Gn of x, xn. So for the leading cumulant, the points are supposed to be to be at different positions. But you extend this function to all the points equal to the same, take the same value. And then this becomes a polynomial in T. So this point belongs to T belongs to. So initially the x were in the interval, so between 0 and 1. So this becomes a polynomial in T. And it happens that you can factorize 1 plus T. And this is a polynomial in T of degree, I forget. So I could f minus 1. And then you can show that f2 of t is 1 plus 2t. f3 of t is 1 plus 4t squared. Phi4 of t is 1 plus 9t plus 21t squared plus 14t3, and I will stop here for phi of t, 1 plus 14t plus 60t squared plus 84 t3 plus 42 t4. So first they are all integers. If you recognize, these are the Catalan numbers, and actually these are the polynomials counting the number of faces of given degree in the associated hadron of dimension n or n minus 1, I forget. So the way you define the associated hadron that of dimension n is that you take n objects that you can, for example, for n equal 4, you will take A, B, C, D, and you construct a graph by seeing how you imagine that this object belongs to some algebra associative, and you want to make product. So the way you will make products is by defining parentheses how you make the product. So if I want to define, that will be one way to do the product, B, C, D. And then I can also do the same product by saying that instead of doing first A, B, and C, I can first multiply B and C and A. So I will have A, B, C, A, B, C, D. Okay, so you look at all the possible parentheses. And then you define a graph by saying that the vertex are the different possible way to define these parentheses, and the edge is when you apply once the associativity rule. It happens this graph is a simplex with different vertices, edges, faces of different dimensions, and this polynomial is the one which counts these phases. So now I think this is proved by Philippe Bian. So to compute this quotient function, we introduce generating function, we satisfy a recursion relation, blah, blah, blah. We don't know structure which is behind this structure. I don't know if it's integrable, but we have a recursion relation for the generating function for that object. And what Philippe knows how to prove is to code this solution in terms of paths, which are in one-to-one bijection with the associated hadron, or decorated version of the associated hadron. But actually, we have a finite structure here because when you look at this quotient function, you can order the point as you want. And so the quotient functions are defined as to permutation of the endpoint. And so it's a refinement of the associated hadron. This formula, these functions which are just made of integers, so they are polynomial with integer coefficient. These integer coefficients are refinement of the associated hadron generating function, and there is not yet a combinatorial interpretation. So that has nothing to do with physics, but this means that there is potentially a structure behind this model, which we don't know. We don't know if it's, we know it's not integrable in generic sense, as we have proved with Fabian at finite n, but maybe it's integrable in a way we don't understand in the continuum limits. So I stop with that, saying that I think there is many things interesting to do, and bon anniversaire Hubert. Je sais pas pourquoi ça marche pas.
So, any questions? Jérôme?
Yes, so it's probably very stupid, but so I'm not used to thinking about these higher moments. So if you wanted to measure them, what would you have to do?
To measure the fluctuation?
Yeah.
It's a good question, yeah. So actually, I wrote a review not recently where I discussed that at length a bit. And so the short answer is that if you want to look at this fluctuation, then you probably have to use ergodicity, and this will, if you then produce a plot of your measurement depending on time, they will converge to the steady behavior, but with fluctuation. And those fluctuations, if you assume ergodicity, will be described by the ensemble statistics that we describe here. So that's, I think, the short answer. The long one is to say that if you want to imagine that you measure the system à la von Neumann, it means that you take your system, you take copies of the system, and from that, so for one given realization of the noise, you take many copies of the system and you produce an histogram. That's what textbooks will tell you. But this histogram will be by itself random because it will depend on the realization. So if you want to make what I did when I describe statistic, I describe statistic of those histograms. Okay. So if you want to make statistic of those histograms, it means that you have to produce the system in the same initial states, evolve the systems many times for each given realization. So you have to sample the noise also with different realizations. That will be super hard to do. No, so it's why I said the short answer, if you want to extract them, is to look at use ergodicity property of the system. Yeah, so otherwise the other step would be to produce different copy, and assume that the different copy are under the umbrella of the same noise, and then you change the noise. That's what you do. That's what you do in mind when you do replica. For example, when I write that you have E of rho t tensor rho t, which is assuming that you have two copies of the system. Actually, what you do is two copies are under the same noise. So you have to produce the same noise here at omega, which acts on the two copies of the system. So for example, the noise, for example, the model I described is actually a long time limit of a spin chain, Heisenberg spin chain, with a noisy magnetic field. So if you take a XX spin chain with a random magnetic field, Brownian one, the long time limit, you can prove it that it's described by this model. So a way to produce something which is very similar to a noise Brownian motion is to take a Brownian magnetic field is to take a magnetic field with a few harmonics which are not commensurable. So you take a magnetic field which is a linear combination of 3, 4, 5 frequencies which are not commensurable. If you look at the plot, it's very similar to a Brownian motion. So that could be a way to realize that you take just your spin chain under a random under your magnetic field which is made of a few incommensurable frequency, and then you look at the behavior of the system.
Other questions?
Well, I'll tell stories for your birthday, but you can imagine Denis and I in an experimental lab, and I can tell you it was pretty exotic, but yeah, we had fun. So you started with this tantalizing idea of quantizing the classical fluctuations, and then H bar disappeared. What happened to it? Can you take some classical limit of what you did? Semi-classical limit?
No, yeah. So there is no H bar, so except that, in a way, classical theory is just related by looking at the mean behavior. That's all what I. So you, or if you want, system size. So if I were putting the H bar somewhere, it's probably. So H bar is an evolution equation, so it will be hidden in the diffusion constant. So the diffusion constant that you get for the density, so you get in the scaling limit. So dH, what I wrote, dHT. When I wrote dHT, just to say that the evolution operator between time t to t plus dt is I dHT. Okay, and I do that because of Ito calculus. So in my formula, dHT was proportional to J, complete constant times the C dag on the Brownian notion. Okay, and then the diffusion constant in the scaling limit is, so G has dimension inverse of time, so it will be G times the UV cutoff square. So the H bar will be here.
So there's no semi-classical?
A semi-classical will just be large system size, or probably there will be a semi-classical theory if you look at the same model but for bosons. Then you may have many particles per site, and you look at the large density, you will have a semi-classical description, be large number. And then when you look at that, you can also say, okay, I will, as Jérôme Pasquale did for GHG, you can try to look at deformation, fluctuation around this classical solution of that, and quantize this deformation. That's one possibility. I don't know what it will describe, at least if I try to.
Any questions from Zoom, Jesper? No? Then maybe we're already late, so maybe we'll thank the speaker again.